Okay, this is college algebra, and we're going to finish our discussion from Unit 7 on power functions. Today we're going to talk about four different situations. How can we model some of this experimental data by observing patterns? For example, by observing how the area of each of the square faces of a cube is found. That a cube has 6 faces, we can deduce that the surface area of a cube is 6 units on each edge, and it has the surface area of S is equal to 6 times x squared square units. Okay, so here's our chart. We're going to determine the first and second differences and determine whether or not a quadratic equation is appropriate. Okay, so we're going to start off with quadratic. So I have 24 minus 6 is 18. 54 minus 24 is 30. 96 minus 54 is 42. 150 minus 96 is 54. All right, those are my first differences. Now second differences. 30 minus 18 is 12. 42 minus 30 is 12. 54 minus 42 is 12. So this is definitely a quadratic equation because my second differences are constant. So we've determined the first and second differences for the edge of a cube and its surface area corresponding to it. What is that quadratic equation? All right, so stat calc, or we entered into L1 and L2, which I have already done. Okay, and then we're going to hit stat calc quad reg. Okay, vars, y vars, function y1. Okay, and that equation is y is equal to 6x squared, and everything else is 0. Okay, and that's exactly what we got right here. Okay, all right, let's take a look at the next piece. The graph and the table below show that the percent of the United States adult population with diabetes, diagnosed and undiagnosed, is projected to grow rapidly in the future. All right, so here we have the years and the percent. Okay, we're going to find not a quadratic model, but a power model that determines or that fits this data. Okay, so we're going to enter the years from 2000 into L1 and the years and the percent into L2. Okay, and I've already done that. So if you need to take a moment to pause the video to do that yourself, and I'm going to find the power reg. So I hit stat calc, and I'm going to scroll all the way down to A, which is a power regression. And let's store this into Y1. Okay, so my power regression shows y is equal to 4.946x to the power of 0.495. Okay. All right, let's see what this looks like. Okay, let's graph this, zoom 9. Okay, there's the data. There's my regression, my power line going through it. Okay, and I want to know what is the percent using this model of people with diabetes in 2015. Okay, I'm going to enter 15 in for X. Now here's the thing. I've already been given the data for 15. It's 18.9%. But it asks to use the model to predict the data. So I'm going to interpolate second calc value 15 and determine, okay, what does the model say? Okay, so I get 18.926094%. Okay, that's pretty close to the actual data. In what year does the model predict the percent to be 29? Well, this data already gives me the year that it is predicted to be 29. But let's use the model. In order to do that, I need y2 to equal 29.0. I need to graph both and find the intersection. Second calc value, no, second calc intersect, enter, 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 and I get that X is equal to 35.49 when Y is equal to 29, and that's the year 2035. So my model is pretty darn close to my data. Okay. This next example talks about cohabiting households. The data in the table below gives the number of cohabiting households. That means that the couple is living together without marriage in the thousands for selected years from 1960 to 2013. We're going to create a scatter plot of the data with X representing the number of years past 1950. Okay, so I'm going to edit my L1 and L2 to reflect this data here. Okay. All right. So now I have entered into L1 and L2 the years past 1950. So that's 10, 20, 30, 35, 40, 45, 52, 54, 57, 58, 60, 61, 62, and 63. And then into L2, I enter the cohabiting households in the thousands. All right, let's see what this looks like. First of all, we're gonna sketch this scatter plot. Okay, so what would that look like? I'm gonna hit zoom 9. Oops. Okay, so I'm going to trace this. So let's say 10, 4, something like this. Okay, it looks like a quadratic could fit this data, but probably a power function would be better. Let's see. Let's start off with a power function because we're asked to find that. So stat calc, I'm going to scroll down to power function. It's A. Hit enter. I want L1 and L2. I'm I'm going to go ahead and store this into y1. The power function, okay, that's a pretty close to 1, but it's not as close as I usually like it. Y is equal to 5.105 x to the power of 1.731. Okay. I wonder, what, let's see what this looks like with it on there. That's pretty good. Let's see if a quadratic would actually be closer. So now we're going to find the quadratic function. Stat calc quad reg is number 5. Let's store this into y2 so that we can graph both of them next to each other. Oh, that R value is actually closer. So I've got y is equal to 2.1 x squared minus 21.79 x plus 314.08. Okay, but on this previous one, my r squared value was 0.97. This one, the r squared value is closer, 0.995. Okay, let's see what would a linear function look like? Stat calc 4 is my lin reg. Let's store this into y 3. Okay, that linear function is probably be about as good as the power function. All right, so let's graph all 3. Okay, here's our power regression. Okay, here's the quadratic regression. That goes through the data a little bit better. There's the linear. Not so good at all, actually. All right, so we found that the power function is a good fit for the data. A linear function or a quadratic function may also be a good fit for the data. The quadratic function may fit the data points even if there's no obvious turning point on the graph of the data points. If the data points appear to rise or fall more rapidly than a line, a quadratic model or a power model may fit the data well. In some cases, it may be necessary to find both models in order to determine which is the best model. I think we're determining here that the quadratic model was the winner. All right, and then this final section, we're going to talk a little bit about purchasing power and inflation. Okay, so inflation causes a decrease in the value of money. So the table that we have below shows the purchasing power of the 1983 dollar based on the consumer prices from 1968 to 2010. Note that a 2006 dollar will purchase half as much as the 1983 dollar. That is, a given good or service costs twice as much in 2006. So we're talking about the 1983 dollar. What is the purchasing power of the 1983 dollar over the course of these years? We're going to let X be the number of years past 1960. Okay, this is going to take us a while to enter, so you may want to pause the video. But I'm going to go through 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 20, 21, 22, 23, 24, 25, 26, 37, 38, and 40. Okay. 2.873. This is really tricky. We're going to have